Hello, hello. Am I coming in loud and clear, everyone? Oh, finally. I forgot to turn my microphone on. So let me repeat what I said at the start. Welcome to week 10. I can't believe that the term is almost over. It's very sad, of course, very sad, because this is our last time together. So, all right. So this is a tutor-led tutorial, and it's a calculus week this week. And the idea is to look at integration. Now, remember, integration is the opposite of differentiation in calculus. And so we'll be working through some problems, and feel free to let me know what's happening in the chat. If you want some extra clarification or explanations, then by all means, let me know how things are doing. And let me know if you're going to do Math 1231 next term, because I can give you some tips on that at the end. All right, so some people may be doing it later in the year, or they may be doing the higher version. Just let us know. So hopefully I will see you there in those courses. But if not, you can always find me online with my YouTube channel and all sorts of things. Okay, so I've done some of these problems in the previous tutorials. I thought today we could talk about integration by substitution. So this part here, integration by parts, and then maybe some improper integrals. Okay, but let's work through some of these, and we can explore them together. All right, so I'm going to start with 16a. Use a substitution to evaluate the following integrals. Okay, so the main difficulty with this method is to actually decide on what a suitable substitution is. And the thing that also complicates it is there's sometimes more than one substitution. You can make different choices. So let's work through this problem, and we can talk about it. All right. So let's go to my document camera. All right. So the basic idea with integration by substitution, as you will know, is to take a difficult or a challenging integral and to simplify it. So let me see if I can integration by substitution. Okay, so the idea, let me just, is that freaking out? I think it's okay. The idea is that you've got a challenging integral. Right? And you make a substitution, okay? And what you get out is a simpler integral. Okay, so that's the idea anyway. So you're taking something complicated and you are making it simpler, or easier to evaluate. Okay, all right, so how do we do that? Well, let's look at an example. So 16a, oops, is something like this. So I'll just call this I for integral. That's what we want. All right. So based on this principle, we could make a bunch of different substitutions. Okay. So the thing that's complicating the integral is this square root sign. So what I'm going to do is let this square root of x be substituted out, and I'm going to introduce this new relationship. Okay, so if I let u be the square root of x, and I can flip it around, I'll get this. Now, what I'm going to do is set this integral up in terms of u. Okay, so I want a du here. So if I take this, I can form what's known as a differential. So if I differentiate both sides, say with respect to let's say just forming the differentials, I guess is a better way of. Okay, you can think of this as saying, well, it's sort of dx du, and you pull the differentials apart if you want to do it that way. All right, so what I'm going to do now is I'm going to replace dx with this in my integral, and I'm going to replace the square root of x with u. Okay. So we're going to have the following. So dx is replaced with this 2u du, and root x is replaced with u. Okay, so now we're like, okay, well, how do we integrate this? Well, it's not as hard as it seems. You can take the u out the front, and now watch what I do. All I've done in the denominator is a sneaky little trick where you add one and you take one away. So then you can break that up into u plus 1 on u plus 1 minus 1 on u plus 1. Okay, so that's a really sneaky but fun trick. Sometimes it can help you avoid things like partial fractions and other things that you don't need to worry about necessarily. Okay, so now I can integrate that term, I can integrate that term, and I'll get something involving u. Now, because our indefinite integral started with x's and we're integrating with respect to x, we want to get back to those x's. Okay, so it's going to be something like this. And I'll put in the c plus c over there. And now let's go back to the x's. Ta-da! Tom, it's a good question. It's a good question. You can see that this is going to be positive anyway, right? So it doesn't really matter. Okay. So if you want to be absolutely sure, yep, you can do it. But in this example, it's not going to matter because u is bigger than 0, and you're adding 1, you're getting a positive thing, right? Does that make sense, Tom? It's a good question. Yeah. So I would say if you're worried about it, put in the absolutes, but here we don't need them. Yeah, well, here x is positive, right? So Tim, that's a good question, but for this to be well defined, x has to be positive. So you don't need the absolute values here, right? Yeah. So these are good questions. These are really good questions. Okay, so the basic idea. The idea. Okay, you want to take a difficult integral and reduce it to a simpler integral through some sort of substitution. Now, here's a good question. This was my substitution. This is not the only substitution. Okay, this is not the only substitution. So for example, if I was to do this another way, right? Oh, actually, I guess I can put it in here. I could let u equal 1 plus root x. That's another way. That way I'm going to get, u on the bottom here when I make the substitution. So it's similar to this substitution, but what's going to happen is I don't get this mess. So let me show you. So if I rearrange it, u minus 1. So if I take that to the other side, x equals u minus 1 squared. And so we're sort of just repeating what we did here and here now. The x is going to be 2 u minus 1 du. Now, if you substitute these in to your original integral, watch what happens. So this is like a second solution now, a second method of solution. Okay, so we sub those things in there. We're going to get this. Now, this is much easier to manage than this. Okay, so even though we made a more difficult substitution, we actually get a benefit here because, you can divide the u straight into those bits. Okay, so now you can just do the integral. So let's see what we get. So that's going to become u. That's going to become log of u plus some constant k. Okay, and now we can go back to what u was. Okay. But wait, people, wait. Have I made a mistake? This answer looks different to this answer. Things on the case. Yeah, the constant is different. This first method is the way they do it in the notes, right? And this is the answer they have in the back of the book. And so they've obviously used this substitution. If you use this one, you get a slightly different looking answer, but it's equivalent because it's just out by a constant. Okay? Yeah. So you don't need to worry about those things. Okay, so whether you choose this form or this form for your substitution, the two answers are still correct and they're consistent with each other. Okay. All right, let's do another one. Let's do another one. So I'll share my screen again in a second. Let's look at the PDF. All right. So I thought we could talk about B and then we'll move on to integration by parts, okay? So B is an interesting one. The problem with part B is, well, you don't want to expand that bracket, right? We don't have all day. Nobody's got time for that. So how do we do it? Can we use a substitution? And the answer is yes. Okay, so let me go back to my document camera and we can look at part B. Okay, so here we've got the integral of x times 5x minus 1 all to the power 19 dx. And the challenge here, we don't want to expand that power to the 19, okay? So one strategy here is to let this linear part inside be your u substitution. So let's try that. Okay, so I've let u be the inside of that. And of course, we can always integrate u to the 19, no problem with that. So if I rearrange this and make x the subject and then compute the differentials, I'll get u plus 1 all over 5. Now I just compute the differentials. So dx is going to be 1/5 du. And now I can take those two parts and put them into my integral. And hopefully, I'm going to get a bit of simplification. All right, so x is that. And this is u. So now you can see, if you step back and look at it, the 1/5 can come out the front. It's just u to the 20 plus u to the 19. We can easily integrate those power functions, right? So we can easily integrate those. Okay, so let's do that. So this is going to be u to the 21 over 21 plus u to the 20 all over 20 plus some constant, c. And now let's get back to our original x's. And I mean, you can clean that up if you want to. But I think that's good enough. Okay. So the basic principle with integration by substitution, you want to take a difficult integral or challenging integral, simplify it using some substitution. To do that, we usually introduce some new variable u that depends on x, and you find the differentials and you make the substitution. Then you compute the integration. Okay. All right. Okay, so that's a little bit about integration by substitution. If you're not sure where to start, just try things, and with a bit of practice, your judgment will improve. And also remember that there's sometimes more than one substitution. All right, let's have a look at integration by parts. So let's go back to the PDF. All right, integration by parts. Use integration by parts to evaluate the following integrals. Now, I've already done part A in another tutorial this week, so I thought we could look at part B and part C, okay? The other ones are kind of many of them are variations on the themes of part B and C. So let's discuss that. So the most important part of integration by parts is making choices. Okay, you're integrating some sort of product, and the rule is like the product rule, but for integration. Okay, for the product rule, you differentiate a product and you have a formula. For integration by parts, you're integrating a product. Okay, so let me show you a little bit about that, and then we can work through a problem. All right, so we've got IBP, integration by parts. You down with IBP? Yeah, you know me. So let's have a look at the integral. So you've got, say, a product of two functions, u and v dash. And the integration by parts formula tells you that this is how you can integrate the product. Okay, so for this you need to choose u, choose v dash, and then compute u dash and v. Okay, so there's four things. There's four things to account for: u, v, u dash, v dash. All right. Okay, so let's do a problem. Let's do part E. I'll come back to the other ones in a minute. Okay, so here, consider please, we have x to the power 7 times the natural logarithm of x. And in this case, you're integrating from 1 to the number e. So you could put those in there, and you'd have a little bracket here where you evaluate these things. Okay. So the question is, which one should I choose to be u, and which one should I choose to be v dash? And the best explanation I can come up with here, you want to make this integral simple. Okay, and even if you make the wrong decision, let's say you mix up the choices, sometimes it doesn't matter, sometimes it does. As soon as you've realized you've made a mistake, then you can just switch the choice. Okay, you can swap the choices around. So I'm going to let u be the natural logarithm of x, that function. And I'm going to let v dash be x to the power 7. Okay? So if they are my choices, then we're going to have, if you use that, u dash is going to be 1 on x. And if v dash is that, the integral is going to be v. Okay? So now we have four things. We've got u, we've got v dash, we've got u dash, and we've got v. We only need four things for our formula to work. Okay? So let's keep an eye on this thing when we do this problem, and hopefully this is nice and simple. So by integration by parts, okay, it is u times v. So that's my u, that's my v. Because it's a definite integral, I'm putting in the limits of integration. Minus The integral of the product of the two things that you just computed. Okay? So what will the product of this be? X to the 7 all on 8. Now, let's pause and have a look at, is this an easy integral? And the answer is yes. This is an easy integral. So it looks like we're on the right path. Okay, so now all we need to do is put these numbers in. So we're going to get e to the 8 over 8 log e, which will just be 1, minus, that'll be 1/8 times log of 1, which is 0, right? Minus this integral. So that's going to become x to the 8 all over 8 times 8, which is 64. And now we just need to simplify here. Okay, so we're going to get e to the 8 on 8. Log, natural log of e is just 1, minus e to the 8, 64, minus 1 on 64. So now we can just simplify this thing. It's going to be 7 times e to the 8 on 64 plus 1 on 64. Okay. So the most important thing I can tell you about this, make your choices. You want this integral or this integral to be simpler. Okay, usually you want it to be doable. If I switch those choices around, would it still work? Well, it might, but you're going to have to find the integral of natural log of x, which you can do, but this part is not going to be simpler, I don't think. Okay, this part is not going to be simpler. All right, let's do another one. Let's do another one. Speaking of integrating log x, let's have a look at part C. So I'll go back to my PDF. Here it is. So part C. Now, I'm confused, everybody. Where is the product? Where is the product? Is it natural log times x? I thought we were integrating products. Can anyone suggest in the chat a strategy here? Because it looks like there's just one function. Then says 1 times log x. That is an interesting suggestion. So if we don't have a product, we can always make a product by inserting a factor of 1. So let's try that. Let's try that. So this is 18 part C. Let me go back to my document camera. So this is now 18 part C. So consider this. Okay, and it's looks like there's no product there. Yeah, Ning Xiao, you're absolutely right here. We're going to do integration by parts, and when we integrate this 1, it's going to become x as you suggest. Okay, so in this case, I would let that be v dash and this function vu. We know how to differentiate log x, no problem, and we know how to integrate a constant. So that's easy as well. So if u is that, then u dash is going to be 1 on x. And the integral of that, just the definite integral, is going to be x. Okay, so let's put our integration by parts formula in effect, and we can compute our integral I. Now this is just a definite integral, so we don't need to worry about limits of integration or anything like that. Okay, so it's u times v minus the product of these two, the integral of these two functions. So we're going to get this, and they're going to cancel off. And this is an easy integral. We're integrating 1. Yay! That is great. So minus, so we integrate that, and it's a definite integral, so we put in the constant. Now, how can I, this is a question for the chat, how do I know I'm right? How do I actually know that this really is the integral of that? Can anybody suggest how we can check our answer? How might we check our answer? Yes, Cynthia, thank you. We can definitely check our answer by differentiating. We would take this, we would differentiate it, and you want to end up with natural log of x. Okay, great job. All right. So I haven't talked about improper integrals now. Let me have a look at one of those. Oh, yeah, okay. So let's go down to, yeah, this one. All right. So let me just share my screen again. All right, so I know this one says V for video, but I thought, I don't know if they do them all, but I thought I would do F here. F is a nice one because it actually combines the ideas we've just learnt with substitution. Okay, so have a look at that, and let me just find my notes here. Got my notes here somewhere. Just bear with me for a second. Yeah. Okay. So we've got this little infinity sign in the integral sign. And what we usually do with these is we manage it away through a limit. Okay. And so let's discuss that, and we can work through it together. All right. So consider the following integral. Okay, so there's a couple of difficulties associated with this problem. Firstly, we have this infinity sign, and secondly, we have this this x log x in the denominator of the thing we're integrating, the integrand. Okay, so what I'm going to suggest is that we make a substitution, and what might that substitution be? Well, if we just write it out like this, we've got 1 on x times this. Okay, and you can see that the derivative of natural log of x is right here. Okay, so what I would suggest is we consider this being our u function. okay? This being our u function, and then seeing what happens, because when we differentiate this, we're going to get something like 1 on x, which is going to be hopefully advantageous. Okay, so let's try it, and then we'll manage away this infinity sign. So, like we did on the previous page, let's compute the differentials. You can see this part is exactly there. Okay, so we can actually replace 1 on x dx with plain old du. Now, how do we manage away these infinity signs? Well, when x equals e, what is u going to be? Well, u is going to be log e. So when x equals e, we have u equals log e, which equals 1. So in our new integral, the lower limit will be 1. And when x goes to infinity, what will log x approach? Log x will also approach. So u equals log x, which will also approach positive infinity. So these are going to be our new limits of integration from 1 to infinity. Okay, so let me label this. I'll just say it's I. We're going to go from 1 to infinity. We substitute out 1 on x dx for du and log x with u. Now, you can see that this is a super easy integral, right? If I integrate 1 on u with respect to u, I get the logarithm, and u's positive here, so we don't need to worry about absolute values or anything like that. Oh, okay. Before I do that though, hang on, before I do that, let's manage away this infinity sign, okay? So when we talk about these improper integrals, this is what we mean. Okay, we integrate on this finite interval and then we let the upper limit go to infinity. So let's do this integral first and then we'll take the limit and see if it exists. Okay. All right, so if we integrate 1 on u, we get log u, and that's from u equals 1 up to b. So I'm going to get something like this. Log of b minus log of 1, which is 0. And now, what is the limit of this? Who can tell me in the chat? If I've got the limit of the natural log of b as b goes to positive infinity, what does this go to? Can anyone tell me in the chat? It does go to infinity. Okay, so that goes to infinity. So does the original integral, thanks Cynthia and Thin, does the original integral converge or diverge? Who can tell me? Does the original integral converge or diverge? It definitely diverges. Diverges. I should probably spell it correctly. The integral diverges. Okay? It diverges. Diverges. Okay. All right, Tom, there's a good question. Can you please explain the step where you turned it into a limit? Well, this is how we define an improper integral, Tom. Okay, what does having an infinity sign there even mean, right? Infinity is not a number. Okay, so it's not like you've got a number in the integral sign like you have in some of the other problems, right? Here, in this problem from earlier, we had finite numbers, right? Just in our integral sign. But with this, who even knows what that means? Okay, well, the way we define it is through this limit. Okay, that's actually how it's defined, Tom. Does that make sense? So when we talk about this, this is really what we mean. We just use this because it's compact and, you know, it's pretty easy to write down. Okay. All right, everyone. I'm going to do one last question, and then I'm going to say my goodbyes. It's very sad, very sad, very sad. I wanted to do a comparison test type question. Okay. So let me go back to the PDF. And I thought we could do question 22, part C. So that one there. Okay. So the idea is use an inequality to determine whether these improper integrals converge or whether they determine if they converge or if they diverge, right? So you could see in the previous question, let me just go back to my document camera just for a second. You could see that we actually worked out this integral and the integral diverged off to positive infinity, okay? So we're sort of asked to do the same kind of thing with these integrals, but by using an inequality, okay? It's called the comparison test. Okay, so consider this. Okay, so what the comparison test tells us is if we can form some sort of inequality based on the function we're integrating, and then we work with this other integral, then we can actually make some conclusions about this one by looking at the thing we're comparing it with. Okay, so what do we compare this with? Our function here, let's say the function is 1 on natural log of x. Okay, so we want to compare that with an inequality with another function. All right, so one simple function that you can use here is the x function, right? This is your x function, and this is your natural log of x function. Okay, so you know that the natural log of x is always less than or equal to, or probably always less than x. Now we've got 1 on x, 1 on log x. So you can flip these around. Yeah, yeah. Well, let's see what happens. So just hang on a sec. Just let me get my notes here for a second. Just want to check something. Just bear with me for a second. Yeah. So 1 on x will satisfy this inequality. So what we've done is we've sort of, inverted this and changed the absolute value around, the inequality around, sorry, okay? So let's let g of x equal 1 on x. And what is the relationship between g and f? Well, that's your f, that's your g. Okay? So let's integrate this smaller function on this interval and see what happens. So consider, please, the integral of the smaller function. Okay, this is an easy function to integrate. We can integrate it and we're going to get the natural logarithm, right? So if I integrate that, I get the natural logarithm of x. So I put in b, I put in 2. All right. What is this limit going to? As b approaches positive infinity, what happens to this function? What does it approach? Yeah, thank you. Which goes to infinity. So we've got this smaller integral, which is positive. And I guess it's less than or equal to, you could make it strictly less than. Okay. So this is what we have. This thing goes to positive infinity. What can you say about the larger integral then? Can anyone tell me on the chat? If this smaller positive integral goes to positive infinity, what can you say about this larger positive integral? It's got this thing pushes that thing to infinity. Okay? So this thing is smaller than that, and this goes to positive infinity. So it's got to push this one off to positive infinity as well. Okay? So by the comparison test, this integral diverges to positive infinity. Okay. So that's our conclusion by the comparison test. So if you have something that's infinite and something that's a bit bigger, this thing's got to be infinite as well, right? Something that's positive and infinite, the bigger thing's got to be infinite as well, okay? All right, so that's just one example. There are other ways of applying this comparison test. Okay, folks, that is it. Well, can you believe it? It's all over. Good luck with your exam. The advice that I have for you is to practice the online past papers. And look, just do the best that you can. Do the best that you can, okay? And thanks for sharing the term with me. I've really enjoyed giving these classes and getting to know you, at least online. And also, I've really enjoyed improving my Asian internet slang. So if you have anything to teach me, feel free. There will be some help sessions next week. So if you want to chat with someone about, getting some revision, then the school will be here. People from the school will be online. Yeah. So just smash that exam. Thank you very much. And yeah, maybe I'll see you later in the year for another maths course. And yeah, just stay safe. And look, I believe in you. I know you're going to do well in that final exam. And yeah, I'll sign off.